So in this lesson, we're going to talk about exponential models. And anytime we see the word model, we know we're generally going to be talking about word problems, modeling real-world applications. So before we talk about some specific applications, I just want to remind you of the formulas that we already have for exponential growth and decay. And then also remember that R in this instance is per time and X is per time. So usually R is going to be like the percent per year, and T would be the number of years. Notice here that these two units match. So if we end up starting to talk about months or something else, then that's going to change how we structure our equation. So let's look at an example of that actually. Our first example is talking about rewriting an exponential function to identify a new rate. So if you will pause the video and see if you can write this equation given what we already know about exponential growth. All right, so this is the function that you should have gotten when you did that based on what we already know about exponential growth. So now notice that this problem is actually asking me to find the monthly growth rate. So I'm needing to change this from years, because that's what I know so far, into months. And we're going to do that using exponent rules. So notice the first thing that we're going to do here is rewrite the exponent to be 12 over 12. That hasn't actually changed its value because that still means 1, but 12 is the number we're picking because there's 12 months in a year. All right, after that, we can use exponent properties to split the exponent, put 1/12 on the inside, and then that's this right here, and then keep the 12 on the outside. And then we can apply that exponent on the inside, which will give us this equivalent equation. And this is helpful because now this inside part will reveal to me the monthly rate. So if I move this decimal back over, this is going to tell me that my monthly equivalent rate is going to be 0.206%. That's the amount of the percentage, the 2.5 percentage that is being applied every month. Okay, so this skill is helpful when we're trying to find an equivalent growth rate or decay rate. Now what we want to talk about is when we are doing specifically compound interest on different terms. So you need to pause the video and go ahead and write down this formula, label it as compound interest and what the various things stand for. Notice this is very similar to the structure that we had before. Really the only thing that has changed is this N value. So N is the number of compounding periods per year. And so there's some common N values that you also need to be writing down. And those would be these values. Annually, N is 1, semi-annually, N is 2, quarterly 4, monthly 12, weekly 52, daily 365. So this is talking about how many times those words, that frequency would occur in a given year. Okay, so if we talk about an example of this example 2, I want to show you a pattern that's going to occur when we talk about compound interest. So this says Tamira invests $5,000 in an account. That's going to be P. That stands for the word principal. That's the initial amount that was invested. Pays 4%. That's going to give me 0.04 as my rate. And the question is asking about T years. So that's going to be our time. 3 years. But then they give me a few different words. So this example is wanting us to compare what happens when we're compounded annually, semi-annually, quarterly, or monthly. All right, so if we take a look at this chart here, they've already kind of got this labeled out for us. Notice what's changing in the equation and where the different values are coming from. Annually, semi-annually, quarterly, monthly. And then really what I want you to notice here is the pattern that's happening. So as we see this pattern of values, notice that the more times that something is compounded, and you look in this table, the higher the amount is. That means when it's saying compounded, it's saying they're evaluating how much money you have, so how much money should they pay you interest on that amount. So if they only look one time a year, then they only get to pay you that interest one time a year. But if they look at your account 12 times a year, they get to reevaluate and pay you that interest 12 times a year, which is then going to increase the amount that you have in your account. All right, so at the very least in your notes, I would maybe write down this second example of semi-annually, this last example of monthly, And then what is written in yellow and blue here, that the more frequently compounded, the higher the output amount. Okay, so there is this concept, though, of compounding continuously. And the problem is continuously would mean an infinite number of times, but we can't plug infinity into an equation and actually get a value out. So this concept, just to give you some brief background, and you don't have to write this down yet, but just listen to what I'm going to show you, or watch rather. If we change this n value, so if n is just 1, the value inside this equation, assuming that the rate is 1, is just 2. As we increase this n value, so you should notice that as we increase this n value, the output value is increasing as we said it would do. But it's actually, the increase is kind of slower and it's getting closer to a specific value. And that specific value that it's getting closer to is this value called E. It is the natural base. So you do need to write this part down. The natural base E is this number right here. And so we're about to see E in some equations. So what I want you to understand is that E is an actual number, just like pi is. It actually has a place on your calculator. You can find it, so you don't have to memorize its value. But it is over there, I think, on the right side near the arrow buttons, in a similar location to where pi is. All right, so if we apply this E number to the formula that we already know, our formula becomes this right here, which a lot of times is referred to as PERT. This is actually one of the more common formulas in the real world when we use compounding. So you need to have this labeled. I'm actually going to outline this whole thing in red. Compounded in continuously, is this formula PERT, and where those things are as they say they are. So you need to have all of that written down. All right, so if we look at an example of how to use this equation, this says Regina invests $12,600. That's going to be what she invests. That's the P. At an account that earns 3.2 annual interest. So this is 0.032 is my R value. Compounded continuously. So as soon as I see that, I know I'm going to be using this PERT formula. What is the value of the account after 12 years? So 12 is going to be my T value. So when we set this equation up, we should be getting something that looks like this down here at the bottom. And honestly, your calculator, I don't know why, but they type in this interest rate to like simplify it. But if it's me, I'm just going to go straight from my calculator. And this is what I would write down in your notes. You're going to go straight from here to this output value. So that would just mean, in terms of this problem, that after 12 years, the value of her account would be around $18,000. All right, so the last application today is for us to talk about how we find exponential models to model data. So basically, if we're given the points, how do we find an equation from that? So this particular example is talking about making soup, and that it's reaching a boiling temperature, so it's getting really, really hot, and then it's cooling off to about room temperature. And the first thing they want us to talk about is what's going to happen when we approach room temperature, and this suggests that we might be getting an exponential decay curve. So notice it is going to be cooling down, but then eventually that should be leveling off, and it should be leveling off around 68 degrees. And that is because that's the room temperature, the air temperature around the data. All right, so also what I wanted to say is because we're going to be modeling data, we need to be getting our calculator out. So if you haven't already, please, please, please pause the video and grab your calculator so you can work along with me, because you definitely need to know this skill. All right, so the first part, you already know how to do this. This is just me saying what we just said, is that as this cools down, we're going to be approaching room temperature, which is going to be at 68 degrees. So we're looking for exponential decay here. Then we're going to go ahead and we want to find the model. So we're going to put this into our calculator. So remember, to do that, we're going to hit Stat. If you haven't cleared, remember you can hit second plus sign. I think option 4 says clear all lists. So we're going to do that, and we're going to enter this data into our calculator. Notice when we do that, let's see if I can scoot this over. All right, so notice when we do that, this is how I entered this data in. Notice that when it says 3.3 here, that needs to be entered. That's 3 minutes and 30 seconds. We need to enter that as 3.5 in our calculator. The same for 7.3 needs to be entered as 7.5. So have these values in your calculator. And then one thing that's going to happen in our calculator is when we ask for an equation, your calculator is always going to assume the asymptote line is at 0. But for this specific problem, we know that the asymptote line is at 68. So what we're going to do is we're going to take our data and we're going to temporarily shift it down by 68. And we could do this by subtracting 68 from every output value, but your calculator will actually do that for you, so I'm going to show you how to make that happen. All right, so we're going to do that using L3. So what you can do, let's see if I can get this shifted over for a second. There we go. All right, what you should be able to do is go up here and highlight L3, and when you hit enter, it will come down here and let you type in a rule for L3. So my rule is going to be L2 minus 68. This L2 on your calculator is above the number 2 and it is blue. So if you hit second and the number 2, this L2 will pop up in this spot, minus 68. And when you hit enter, your calculator will then replace the L3 values with it will actually just populate these values with new values, which if you notice, they are all 68 lower than the original values we were given. Okay, so now we're going to use that to find our equation. So we're going to go back into stat, and we're going to go into the calculate menu, and if you scroll down, I think it's pretty far down there, there's one that says EXP regression, and that's exponential regression. That's the one we want to choose. Now this part is a little different. Usually you just sit there and hit calculate until it gives you an answer. In this regard, it automatically has L1 and L2 set for our X and Y, but remember we just changed this and we don't want to use L2 anymore. We want L3. So where it says Y list, you need to change that to say L3. And then we're going to calculate, and in my calculator it gives me this equation. And then just a comment there, I always carry 2 decimal places. It might look like I'm carrying 4 here, but remember with percentages we end up moving this back over, so on the inside then 4 decimal places would be appropriate. And the only thing we have left to do is account for the fact that we shifted it down by 68, so now we need to go back and shift our function up by 68 to account for that change. So this would be our model that would be used to replicate this data. And then we could use this model to answer questions. So for instance, this particular question asked how long would it take for it to reach 80 degrees. So we could use our table and figure out how long would it take for it to reach 80 degrees, or what would the temperature be if we only waited 30 minutes or whatever else. So you need to make sure that you have good notes about how to use your calculator and about the equations that we learned today so you can use them in class tomorrow.